Hey everyone! In this video, I'm going to talk about summarizing bivariate relationships. And in many cases, these bivariate relationships are relationships between two variables that are both on the continuous scale. And if we have such two variables that are both continuous, the most basic way of kind of exploring that relationship between those two variables visually is to plot them together in what is called a scatter plot. And essentially that just means plotting each individual data point in a two-dimensional grid for both where one variable is represented on the x-axis and the other variable is represented on the y-axis. In R, we can directly achieve this by using the plot function. And we're going to keep using our example of the Afghan survey in the southern provinces in 2011 in Afghanistan. And what we're going to do here is we're looking at the bivariate relationship between the average age of a village and the average education level of a village. So to what extent is the age distribution in a given village, the average age distribution related to the average education level in that village. Okay. So the first thing we're going to do is we compute the average age for each village ID in our survey. So we're using the tapply command again, which you've seen before. We're just computing the average age for each village, as well as the average education in years for each village. And of course, this is not necessarily from a substantive point of view, not really, we're not really interested in any type of, causal effect here. And of course, there will be a relationship because, if you have a very large young population and they're still in school, for example, that would result in a positive relationship. But we'll just use this as a straightforward kind of toy example. So if we want to look at the distribution of those two variables together in our survey, again, we use the plot command and we include both variables as arguments in our plot call. And we can set the labels for the x-axis and the y-axis accordingly. The resulting plot looks like this. We have average age on the x-axis ranging from around 18 to 47, and then average education in years ranging from 0 to 11 years. And we see a positive relationship. If the average age tends to be higher in a given village, the average education level in years tends to be higher as well. Oops. Sorry about that. All right, so that's just one way to kind of inspect the relationship visually. We can also kind of use different measures to summarize this type of relationship, this linear relationship between two continuous variables. And one key statistic to measure this linear relationship is correlation, right? So correlation kind of tries to quantify, on average, how do two variables move together? To what extent does one variable being higher tend to also imply that the other variable also takes higher values. And that's what we mean by a positive correlation. When x is larger than its mean, then y is likely to be larger than its mean as well. And a negative correlation is the opposite type of relationship, where when x is larger than its mean, then y is unlikely to be larger than its mean. Okay, so that would be a negative correlation. In other words, visually, if we go back to the kind of the data cloud that we saw in the previous slide, a positive correlation means that there's the data cloud slopes up, and a negative correlation means that it slopes downward. Correlation doesn't only tell us something about kind of the direction and whether there's a positive or negative relationship, but it also tells us something about the strength of this relationship in the sense of how tightly the data cluster around a line that kind of summarizes that relationship. We're going to talk about that in more detail as we go forward. But for now, we're going to just look at the mathematical definition of the correlation coefficient, at least one way to kind of conceptualize it, which is you can think of the correlation coefficient as the average of the products of the z-scores of both individual variables, right? And that kind of gives you an idea of what we kind of the underlying intuition that I mentioned previously, where when x is larger than its mean, y is larger than it's likely to be larger than its mean when we have a positive correlation, right? So that means for every observation where xi is larger than the mean, if yi tends to be larger than its mean as well, then the term on the left and the term on the right tend to both be positive. And that means the product is also positive. So that means the correlation coefficient tends to be positive. Of course, when both are negative, because both xi and yi are smaller than their mean, then they tend to be both negative. And so negative times negative is, again, the product would be positive, right? So positive correlation kind of implies that when one variable tends to be higher, the other tends to be higher. And when one variable tends to be lower, the other one tends to be lower. Negative correlation, again, think of it in the logic of this z-score for each individual variable. If one variable, if x tends to be higher than its mean for that observation, y tends to be lower than its respective mean. So then this product tends to be negative, right? A positive value times a negative value is a negative value. So that leads into a negative correlation. So you can see kind of if you look at the mathematical notation and kind of conceptualize this as the mean of products of z-scores, and there, we'll look at different ways to kind of define this mathematically and rearrange this. But if you think about it this way, it kind of helps you kind of get around this underlying intuition of what a negative and positive correlation ultimately means. Note here that we're dividing this average by n minus 1, and similar to the standard deviation, sometimes we divide by n rather than n minus 1, but ultimately this is the n minus 1 is basically just a simple correction for the sample estimate ultimately. All right, a couple of properties of the correlation coefficient. The correlation is bound between -1 and 1. So -1 is a perfect negative relationship, negative correlation, and 1 is a perfect positive correlation. The order of the variables does not matter. So the correlation between x and y is equal to the correlation of between y and x. And the correlation coefficient is also not affected by changes of scale, right? So, we can think of this as, if you look at the correlation between temperatures and convert Celsius into Fahrenheit, or if you look at correlations between, suppose you're looking at the relationship between someone's height and body weight, for example, right? Clearly a positive correlation, and that correlation will be the same regardless of whether you measure height in centimeters versus inches and weight in kilograms versus pounds, right? So these are all linear transformations of the scale, and the correlation itself is not affected by these linear transformations, which is what is expressed here. And one thing that is really, really important to keep in mind is that correlation only measures linear association, right? So the absence of correlation does not mean that two variables are not related or associated with each other at all. It just means that they're not linearly associated. So for example, once we have a curvilinear relationship or something like that, then there might still be an association between two variables. It's just not a linear association, and the correlation might still be 0. If we want to compute correlations in R, we can use the COR, so COR function in R, and this function either takes two variables as an input or a matrix of multiple variables as an input in order to provide a correlation matrix of all individual pairs of variables in that matrix. Okay, I'm going to show you an example in a second. Once we talk about correlation matrices, it's important to think again about how we handle missing observations, and we can kind of define R's behavior here by using the use argument. If we set the use argument to pairwise, that means we use the available case analysis, which means we're dropping, when computing the correlation between two variables, we're only dropping observations that have a missing value on each of those two variables that we're considering, and we don't care about missing values on the remaining variables that are included potentially in that matrix. As opposed to using the complete.ops option, which would mean that we're dropping all observations that have a missing value on any of those variables, right? Yeah, I just realized that this is in there twice, but that's fine. So how do we do this in the context of our survey data? In our case here, I want to look at the correlation. I want to look at the average income across villages. So the first thing I'm doing here is I'm converting if you look at the original data set, the income information is actually a factor variable, or it's a character, a string variable. I'm converting this variable to a factor, which means that it has an inherent order, and I'm specifying the order here from yearly income, household income of $2,000 to up to over $30,000, and then I'm computing the average income in the sense of average income category. So this is now ranging from 1 through 5, and we're computing the average income category across villages. The average income category across villages, right? And so here this variable has missing values on some for some villages, because in some villages some of the respondents did not provide income information. So we have missing values here. Just to illustrate this example, let me move myself up here a little bit. And so if we now look at the correlation matrix between those three variables, the average age, average education, and average income, this is now a matrix as an input to this correlation function, and we include the option use equals pairwise. Then basically all observations that if we're looking at the correlation between income and the other two variables, then these missing variables on income are excluded, but that does not mean that these observations are also excluded if we're just looking at the correlation between age and education, for example, here. Right? So the matrix here is a matrix where in the diagonal the correlation is of course 1 because it's the same variable, average age and average age. And then the off diagonal we see the correlation between each of those individual continuous or quasi-continuous variables, right? So age and education is positively correlated, as we've seen before. Average education and average income is also positively correlated, but the correlation between average age and average income is much lower, almost 0. Okay. And last important technique to compare two distributions to each other is the quantile plot, or oftentimes just called QQ plot. And the QQ plot allows us to kind of plot the quantiles of one variable against those of another variable, and they help us to compare distributions from different data sets and see whether they're kind of similarly shaped overall. In the QQ plot, the 45-degree line indicates the equality of two distributions, right? So if the QQ plot is just a straight, diagonal line, then both distributions are kind of similarly shaped, right? And as soon as you have a deviation, then then one distribution is either more dispersed or less dispersed and things like that, right? So just to go through one example here, I'm looking at the QQ plot of the age distribution in two different provinces. We have Helmand and Coast. And so in order to run this QQ plot, I'm including those two variables as arguments, and then including an argument for the labels for the x-axis and the y-axis. And the resulting plot is this plot. And so the important thing is to kind of go through the underlying logic of what this QQ plot does, right? So ultimately what this QQ plot does is it separates each distribution, the age distribution in Helmand and the age distribution in the Coast province, into separate quantiles, okay? Remember, the quantiles are basically just the so this is kind of the tail end of the distribution, and so we're kind of separating the overall distribution in equally sized kind of bins, right? And so we can say, for example, like the highest age, the largest age in Helmand is about 70, as well as the age, or the end of the distribution of the age in Coast is also about 70, right? So if all these points are on this 45-degree line, that means that both distribution have approximately the same shape. As soon as one line, or as soon as this line kind of moves away from this 45-degree line, we have what we see is that one line, one distribution is more or less dispersed than the other. Okay, so here we see that the points are less steep than the 45-degree line. Okay, they taper off here a little bit, and that means that the distribution on the y-axis is ultimately less dispersed than on the x-axis, right? And so kind of to understand why this is the case, kind of think about what each of these individual points mean, right? So this is kind of the third quantile, right? So the third largest bin of the age distribution in Helmand and in Cost. And we see here for this individual, for that individual quantile, we see that the age here is around 69 for Helmand, and the same kind of quantile in the age distribution of Coast is around 60, so is lower, right? So the same quantile has a lower value in one in Coast in Cost than in Helmand, which means that the age distribution in Helmand is more dispersed, and the age distribution in Cost is less dispersed, the range is less wide, okay? So if these two, this would be even more clear if these two dots were down here as well, then ultimately the age distribution in Cost would have, you know, a smaller range as well, for example, okay? So we're gonna look at QQ plots actually in the next assignment in order to kind of evaluate distributions. The key thing to kind of keep in mind is that this is useful to compare distributions across different data sets, right? So when we look at scatter plots and correlations, we're looking at different variables in the same data frame, where one observation has a value on the x-axis and a value on the y-axis, and we're looking at the correlation between the two. The QQ plot allows us to evaluate shapes of distributions from different types of different data sets ultimately. Okay. All right, that's it for bivariate relationships. In the next video, I'm going to talk about measuring ideology and political polarization.